So your first step in solving these is to find a reference angle. Your next step, I don't know whether you want to call it second out of 3. You can have 4 steps or 5 steps depending on how you want to break it down. But the next thing you need to do is identify where the terminal arm can lie based on the trigonometric information you were given. So let's put those two together with 3a. Question 3a asks you to solve the trigonometric equation 2 cosine theta minus root 3 equals 0. So the first thing you have to do is kind of prep that equation. By moving the root 3 over and dividing both sides by 2 and getting cosine of the rotation angle is root 3 over 2. Now, I'm perfectly aware that many of us can just go right to the unit circle and pretty much answer this question. But if you follow these steps, now what we want to do is find the reference angle. Remember, that theta is not the reference angle. That's the rotation angle. That's what we want. And when you use your calculator to find a reference angle, this is where you go second, in this case, second cos. Even though this question, everybody, asks you to get an answer in radians, because when you look at the domain, it's 0 to 2 pi radians. If you want exact values, you want to put your calculator into degree mode because you're not going to recognize radians in decimal form. So now that I'm in degree mode, I can take the inverse cosine of the square root of 3 divided by 2. Watch your brackets on this, because when you take the square root, it's going to force an incoming bracket on that argument of 3. You've got to close that before you divide by 2. Anyway, what we get is a reference angle of 30 degrees. But since we're talking about using radians, you're not going to use 30 degrees. Look, I suppose you could do the whole thing in degrees and then convert them all to radians. But I think it's simpler to simply say that the reference angle, which is not our answer, is pi over 6 rads. I mean, you should know 30 degrees is pi over 6. So that's one of the first things you have to do, find the reference angle. Then what you need to do is identify the quadrants in which the terminal arm of the rotation angle lies, and we had cosine of theta was positive root 3 over 2. So you need to look at your 4 quadrants and identify which 2 quadrants cosine of theta is positive. Cosine of theta is x over r. Right? This is equal to the x coordinate on the point on the terminal arm over r, which is the distance from the point to the origin. So how can cosine of theta be positive? Well, it can be positive whenever x is positive. And x is positive in quadrant 1 and quadrant 4. X is positive in this quadrant and in this quadrant. So we sketch a terminal arm in quadrant 1 with a reference angle of pi over 6 rads. We sketch a terminal arm in quadrant 4. I'm not sure why I wrote 2 there. This is 4. We sketch a terminal arm in quadrant 4 with a reference angle of pi over 6 rads. Again, you know, these little details I think are important in understanding the math. There's no direction to that angle. It's just an angle. Theta, which is what we are asked to find, is from 0 to 2 pi. So these 2 arcs are the 2 values of theta that are answers to the question. So theta equals pi over 6 for quadrant 1. And for quadrant 4, theta equals 1, 2, 3 pi over 6, 4, 5, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And you can write 11 pi all over 6, or you can write 11. pi over 6. It's up to you. So take a look at your work now. Does anybody have, this is the answer. Does anybody have any specific questions you would like me to go over? Go ahead, Marcel. 5D. So 3 sine x minus 5 equals 5 sine x minus 4. And I'm glad you asked about this. I also want to briefly go over f as well. I had pulled these examples out of your lesson where we had, I call them weird, wacky domains. But I think at this point in time, now that we've had some practice with the basic stuff, we can talk about them. One of the things you have to do here, first of all, with D is get the equation into the form. This is not a very mathematical way to write this, but you have to get it so that you have a trig ratio of an unknown equals a number, so you can go inverse trig ratio of that number. And what that means is we have to move the sine x's to one side and the numbers to the other. So right now we have 5 sine x on the right. If I subtract 3 sine x from both sides, that leaves me with 2 sine x on the right. And I think you know me by now. I would much rather arrange an equation so my unknown is positive. So that's why I decided to move my trigonometric terms to the right side. I also have to add 4 to both sides, so I end up with this statement. I have negative 5 on the left. I'm going to add 4 to negative 5 and get negative 1. And now, finally, we're ready to find a reference angle. So are you okay with getting to that point? How many of you, I'm just curious, how many of you can pretty much look on the unit circle and tell me that it's these two locations? I mean, if you can do that, that's really the goal. But if we stick to the tried and true method, which will never let you down in solving an equation, we're going to find the reference angle. I'm going to call it x reference by taking the inverse sine. Remember, that's not an exponent. It's just, I wish whoever invented that had not invented it. I wish we were forced to write. I wish we were forced to write that x reference equals inverse sine of 1/2. It's not an exponent. Notice that I'm not including the negative in there. Now, whether we want to work in degrees or not for a final answer, we want to be in degrees to find the reference angle whenever we're talking about exact values. And do you get 30 degrees? Okay, so the reference angle is 30 degrees, and unlike the previous question, Marcel, where I wrote pi over 6, I'm going to write 30 degrees because my domain is given in degrees. So now what we're going to do is use the fact that sine was negative to determine the two quadrants. And this next bit of business is really subtle but important. I'm going to do this so I can find the locations, not the rotation angles. I want to just identify where the terminal arm lies. And since sine is negative, Marcel, which two quadrants can the terminal arm end in? 3 and 4, excellent. Where the y coordinate is negative because sine is y over r. Right? This is equal to y over r by definition. So we're looking at where y is negative. It could be in quadrant 3, and it could be in quadrant 4. If we draw the terminal arm in quadrant 3, it's here. If we draw it in quadrant 4, it's here. This is a 30-degree reference angle. This is a 30-degree reference angle. Now, normally in the majority of these questions, you're going from 0 to 360. Okay? And what we would say is that this is the reference angle, or sorry, the rotation angle, right? And we would say this is the rotation angle. Now, if we do that, give me 1 second. If we do that, for the one that's in quadrant 3, we will get theta equals 210 degrees. Would you agree? Okay. And if we do that for the one that's in quadrant 4, we would get 330 degrees. And I think you're okay with that. But look at what the domain is. The domain says we want to go from and including negative 360 degrees up to and including 180. So represented as a kind of a line graph, it can be any angle that's equal to this, greater than that, or less than 180, but it can't be 180 because if you look carefully, there's no equal to as part of the inequality with the 180. So is 210 in there? No, 210 is over here someplace, right? Is 330 in there? No. So I'm going to show you right now what I think is the best way to do this. $210 is not in there. Would you agree? Are there other angles that put you in the same place? That put you in the same place as this? Well, yeah. 210 plus 360 degrees does. If I can get my calculator going. How many of you see the futility of doing this, of adding 360? Meaning it's a waste of time because we're already at 210, which is outside of the domain. So why would we add 360? But if we take 210 and subtract 360 to get a coterminal angle, we get negative 150. And I think everybody understands that you could have just looked at the diagram and said, well, I can go negative 150 to get there. So this is not an answer, but this is. And if I wanted to, Marcel, I could now take the negative 150 and subtract 360 again. But now I see I'm outside of the domain. But imagine that this was... It isn't. But imagine it was 720. Negative 720. Then this number would also be in the domain. So what we're doing, if I can summarize this, I'll get back to what it really was, is you're taking this angle and this angle, the ones that you found and you would normally find, and you're adding or subtracting full revolutions to get any angles that are in that domain. So the only angle that will give you this terminal arm in quadrant 3 is 150. Is there an angle that will give us this terminal arm in quadrant 4 that's in this domain? Well, 330 doesn't, but if you subtract 360, you get negative 30. So negative 30 does. Have I answered your question? Okay. Any other questions? Go ahead, Ian. Ian? Okay. For B? So cosine of theta equals negative 0.9. 0.19 rather. We want a series of answers or a set of answers that go from and including 0 up to but not including 2 pi. This is in radians. Everybody, since we want decimals, it might be useful for us. It's not going to be in this case, but it might be useful in other cases for you to recognize that 2 pi is approximately 6.28. If you take 2 times pi on your calculator, you're going to get pretty close to 6.28. So we want answers or numbers that are equal to 0 degrees or up to, but not equal to 2 pi. It's a fancy way of saying a full revolution. We have to find the reference angle, locate the quadrants, figure out the rotation angle. So can you please, everybody, calculate the reference angle here on your calculator? And we want answers in radians in decimal, so we shouldn't be frightened of being in radians and getting decimal answers. We don't want to work in degrees and convert. So we'll take the inverse cos of 0.19. Hopefully you've already got it. The answer is not the answer. The reference angle is 1.37. We don't put the negative into the calculator. If you did, you're going to get a bigger number. Okay, I don't want you to worry about that because I don't want you to do that. Don't worry about what that bigger number is. So the reference angle is 1.37. We're talking here about quadrants where the cosine is negative, and since cosine is x over r, it's wherever x is negative, which is to the left of the y-axis. We're talking about quadrant 2 and quadrant 3. Look, I didn't write down, was it 1.37 reference? So theta reference is about 1.37 rads. I do, but you probably don't know how big of an angle 1.37 rads is. It doesn't matter. You're simply going to sketch a terminal arm in this quadrant, and you're going to put 1.37 rads as the reference angle. You're going to sketch it in this quadrant and put 1.37 rads as the reference angle. The rotation angles will be this and this. That's theta. So how do you determine theta if it's in quadrant 2? You're going to take pi radians and subtract 1.37 radians. And that literally means on your calculator taking pi minus the reference angle. So theta in quadrant 2 is 1.76 rads. That's an answer for theta. And in quadrant 3, you're going to have to take 180 degrees, rather pi, and add the reference angle. So you'll take 3.14 plus the 1.379. So in quadrant 3, it's 4.52 rads. Are we okay with that, Ian?
Yeah, I just forgot the negative.
Okay. William, did you have a question? No? Jonathan? Somebody over here, I thought.
Oh, I had the same
The
question.
same question. Okay, that's good. All right, let's move on. So this is the next lesson in your handout. It's looking like it's on page 19. Thank you. And this is more complex trigonometric equations. The nice thing about this is it has to do with my philosophy in teaching high school math. At every point in high school math, whether it's calculus or math 30 or math 20, we take problems that are presented at that level and we turn them into simpler problems. Okay? So that's always our goal. For example, we could go back and look at a question that nobody asked about. Nobody asked about this question. Let me get rid of all this stuff. Nobody asked about this question. And that's not a criticism. It's just a statement of fact. Nobody was wondering about that question. Well, If you show this question F here to a Math 20 student, they don't understand what it means because they've never been taught what cosecant is. But we've been taught that cosecant of theta is equal to the reciprocal of sine of theta. And that means that sine of theta is the reciprocal of cosecant of theta. What that means is sine of theta equals the reciprocal of negative 1.57. And all of a sudden, we've turned that question from a Math 30 question to a Math 20 question, because this is a question that would be on a Math 20 exam in trigonometry. And we teach you in Math 20 that you find the reference angle, you locate the quadrants, and you draw the rotation angles. So keep that in mind as we go through this lesson. We are always trying to make things into a simpler problem. So what are we solving here? More complex trigonometric equations. Whether it's over a specific domain like 0 to 2 pi, or negative pi to pi, or whether it's over a domain of all real numbers. Usually, but not always, what complex means in this context of this lesson is it's quadratic. So think about that. We're going to be solving trigonometric equations that are also quadratic, or quadratic equations that are also trigonometric. And I'm going to review some things here about quadratic equations. And this is not in your notes, but I think this is crucial. And we don't necessarily have enough time to focus on this in Math 20. I should probably make time in my Math 20 class. On the board right now, or the screen, we have three different quadratic equations. This has nothing to do with trigonometry. We have 2x squared minus x minus 1 is equal to 0. We have 16x squared minus 4x equals 0. And we have 3x squared minus 5 equals 0. These are all quadratic equations, everybody, because they have a quadratic term. It's a polynomial with the highest degree of 2, so we call it quadratic. And if I said to you in Math 20, solve this quadratic equation in the top left corner, you notice that this equation has every term represented. It's got the degree term, degree 2 term, it's got the degree 1 term, and it's got the degree 0 term. It's got the quadratic, the linear, and the constant. If I said solve the equation in the top right, you notice that it has a quadratic term and a linear term, but no constant term. And then if I say solve the quadratic equation at the bottom, it has a quadratic and a constant, but no linear. And I'm pointing this out to you because there's three different ways that you solve these three different equations. Each one has its own method. When you solve the equation in the top left, you factor it. And then what you do is you set each of those factors equal to 0. Here's a perfect example of what I'm talking about. This equation, 2x plus 1 equals 0, I'm not familiar with grade 8 and grade 7 math curriculum. I should be, but unfortunately I'm not really. But definitely that's grade 9. We would expect every grade 9 student capable of passing grade 9 to be able to solve this equation. So all of a sudden we've gone from, on the top line, basically a grade 11 question, down to the bottom line to a grade 9 question. And you solve this, right? You subtract 1 from both sides and divide both sides by 2. You add 1 to both sides, you get those two solutions. If I say to you now, how do you solve this equation on the right? It's a little disappointing that a lot of Math 20 students forget how to solve that. They start thinking it's going to factor like we did the factoring in the first one, but it doesn't. You just factor out a common factor. So if you have no constant term, you take out a common factor. And there will always be one because those two terms have to both contain x. And then we can set 4x equal to 0, and we can set 4x minus 1 equal to 0, and we can solve each of those little linear equations to get answers. If, on the other hand, there's no linear term, you don't factor. You rearrange it. I can add 5 to both sides and divide both sides by 3, and then plus or minus the square root. And I'm putting this up here and including it in the video so you can maybe watch it later if you want, because I'm going to refer back to it. Sooner or later somebody's going to ask a question about a trig equation, and I'm going to say, well, is it quadratic? The answer is yes. What kind of quadratic? Is it a full-blown quadratic equation? Is it one of these ones that's quadratic, but really, other than the plus or minus, it's a junior high problem? Or is it one of these which is still factorable, but not as a factor of two binomials? Because there's 3 different ways to solve these. All right, let's get to the lesson. Warm up. Solve these equations. Well, this is like stealing candy from a baby. 2x minus 1 equals 0. I'm going to actually show a step here that I don't think many of us would show. I'm going to add 1 to both sides. So what I get is x is equal to 1 over 2. No problem. Here I subtract 1 from both sides. I get x is equal to negative 1. No problem. Here I have a quadratic equation. It's what I call a full-blown quadratic equation. We just went over this. How do you solve a full-blown quadratic equation? You factor it. By the way, this equation on the top left corner of the screen here is not the one we're solving. It's subtly different. So we're going to factor this into 2 linear factors. It must be 2x and x to multiply to give the product of 2x squared. It has to contain a 1 and a 1, regardless of which one's positive and which one's negative. The numbers themselves have to be 1. And we need a positive 1x in the middle. So when I FOIL this out, I'm going to need to have 2x and negative x to give the 1x. Don't forget this is equal to 0. So now we have 2x minus 1 equals 0, and we have x plus 1 equals 0. By the way, the reason why this works, we get x equals a half. We get x equals negative 1. The reason why it works, and this has been taught to you, but I'll just say it one final time, is there's a multiplication symbol between these 2 factors. So if this is 0, it doesn't matter what the other factor is. When we multiply it, we'll get 0, which is what the equation is saying. And the same argument can be made for why we set x plus 1 equal to 0. So again, a review here. To solve a trigonometric equation that's quadratic in nature, one of the things we can do is factor it. So you're going to be factoring trigonometric equations. And the basic thought here, or idea, or concept is that if the product of 2 linear factors is equal to 0, then if you set one of the factors equal to 0, you'll get an equation. If you set the other factor equal to 0, you'll get an equation. I want to point out to you, the equations we're going to get are the ones we were solving yesterday. So we're going to be taking quadratic trigonometric equations and turning them into 2 linear trigonometric equations that we were able to solve yesterday. All right, so examples, solve. Now we do have to talk about something first. What does this mean? First of all, it's pronounced sine squared of x. What it means is sine of x quantity squared. So we have in this equation, I'm going to rewrite the equation, and I'm going to rewrite it as 2 times sine of x quantity squared. We're not going to do that. We have to graduate beyond that and just understand that we can write 2 sine squared of x. But I'm doing it for the first example. And this is equal to 1 plus sine of x And I'm going to put a coefficient of 1 in front of the sine of x. So I look at that, and from a mathematical standpoint, I have something with a variable squared, I have something with the variable, and I have a constant. It's quadratic. And when you solve a quadratic equation, you zero the equation. So we're going to have 2 times the sine of x quantity squared. I'm going to have to subtract 1 sine of x, and I'm going to have to subtract 1, and this is equal to 0. So now I'm going to factor this. I hope that everybody sees how this equation is similar to this equation. I mean, it's similar to this equation. Remember this, a or cat, or sine of x, these are all just squiggles on paper that represent some mathematical thing that happens to be variable. So if I were to ask you to factor 2a squared minus a minus 1, you'd put a and a in both of the binomials. Sorry, you'd put a and 2a in both of the binomials, or in each of them. So we're going to have 2 sine of x and sine of x. And just stop for a second and foil that out so far in your head. Hopefully you'll see that when you take 2 sine of x times sine of x, you get 2 sine of x quantity squared. The numbers that we have to put in these two places have to multiply to give the 1. So what I'm about to write in green is not necessary to write, but some of you might benefit from it. When I FOIL this out, my first will be 2 sine of x times sine of x, which is 2 sine of x quantity squared, and that's what I want. I want that. So that's good. Personally, I don't feel the need to check that, because that's why we put those two things there, so that we would get 2 sine of x quantity squared. If I multiply out the last, I get 1 times 1, which is 1, which is what I want. I know it's negative, but we'll worry about the negative when we need to. When I multiply out my outer, I get 2 sine of x, 2 sine x times 1. My inner, I get 1 sine of x. And the question is, can I combine these in some way? Can I combine those in some way to get that? And the answer is yes. If the 2 sine of x is negative and the 1 sine of x is positive, that would give me the negative 1 sine of x. Now I say to myself, well, how would I accomplish that? How do I get negative 2 sine of x? Well, the sine of x came about as the product of this and this, so to make it negative, I'm going to make this 1 on the right negative. Everything below that red factored equation is not necessary in a written response or in any of the work you do. Okay? Now, what you could have done, and I recommend this for, I would say, somebody who is struggling a little bit. What you could have done, if it's easier on your brain, is rewritten the equation as 2a squared minus a minus 1, factored this. And I know that for most of us, we look at this and go, it shouldn't make a difference. If you can factor this, you should be able to factor that. But it does. So what you could do is change the question to this, and then change the a's back to sine of x to get that. Okay. Anyway, what we now have is 2 sine of x plus 1 equals 0. And we have sine of x minus 1 equals 0. And these are two equations you could have solved yesterday. Find the reference angle, locate the quadrants, determine the rotation angles. So again, what's in green is just a check of our work. The red is our work. So this equation, when we rearrange it, becomes sine of x equals negative 1/2. This equation becomes sine of x equals 1. And I am going to take a turn here and almost force you to think of the unit circle. Because a sine of a rotation angle being negative 1/2 is where the y coordinate on the unit circle is negative 1/2. Something you need to be very aware of, the x in this equation is not an x coordinate, it's a rotation angle. It's theta. But where, it's not a great placement of my axes, let me fix that. Where is the y coordinate negative 1/2? Here, which means at this position, and here at this position. Now I'll do the reference angle approach in a minute, but what this is telling me is that the rotation angle is 7 pi over 6. Help me out, were we asked to work in radians here? Did it say 0 to 2 pi? Okay. 7 pi over 6 because we have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6, 7 pi over 6. We also have 8, 9, 10, 11 pi over 6. Well, I'll finish this. Where is sine of a rotation angle equal to 1? Well, sine is the y coordinate. It's equal to 1 here. So this is the third position. What is that? So we had 7 pi over 6. We had 11 pi over 6. What is this? It's pi over 2. Now what I'm going to do, and I won't do it by writing a whole bunch of stuff, but I'm going to do it on my calculator as reference angles. So for sine of theta equals negative 1/2, I'm going to take the inverse sine of 1/2. And I get a reference angle. Okay, so wait. I get a reference angle that's unrecognizable to me. That tells me I'm in radians. I'm going to put my calculator into degrees. And the reference angle is 30 degrees. In which two quadrants is sine of a rotation angle negative? Well, that's where y is negative. That's quadrants 3 and 4. Well, that's here with a reference angle of pi over 6 or 30. That's here with a reference angle of pi over 6 or 30. Even if you can't handle the unit circle approach, you should appreciate right now how much quicker it is to just look at the unit circle and say in these two locations. We will get the same answers. What if you looked at this equation and you looked at this equation where sine of x equals 1. Well, what's the reference angle? This gets a little strange. The reference angle is 90 degrees. So then you say, in which quadrants is sine positive? Well, that's where y is positive. That's quadrant 1 or 2. But if you have a reference angle of 90 degrees in quadrant 1, it's up here at the top. If you have a reference angle of 90 degrees in quadrant 2, it's also at the top. So you're still going to get this one. Now, that's A. Any questions with solving that equation? The answers are in green at the bottom of the screen. All right, what's the general solution? Well, we could write the rotation angle is, we had pi over 2. We could write plus multiples of 2 pi. We had 7 pi over 6 plus multiples of 2 pi. We had 11 pi over 6. 11 pi over 6 plus multiples of 2 pi. Of course, n is an element of the integer number set. Just a second, please. So this is one way you could write the general solution. And I'm going to tell you that if it were a multiple choice question, this may be the answer or it may be different. If it's a written response question, you can put this and get full marks, or you can put something different. And the thing that you can put different is only possible because of where these three locations land. It won't always be the case that you can do what we're going to do. But by the way, it's very helpful for you to be able to look at all three on the same diagram, because then you can see that these three angles are all 120 degrees away from each other. And since they're all 120 degrees away from each other, what I can do instead is just say the solutions are pi over 2 plus multiples of 120 degrees. And I will hit all of them again and again and again. So we could put or x equals pi over 2 plus multiples of 2 pi over 3. 2 pi over 3 is 120 degrees. Again, where n is an element of the integer number set. Ian, question?
For all of them, if you add 2 pi, won't that be outside of the domain?
You're asked in this question to write a general solution. By definition, general solution means that. So when you look at the objectives at the top of this page, one of the objectives is to solve a more complex trigonometric equation over a specified or specific domain. That was A. To solve the same equation over the domain of all real numbers, that's called a general solution. I think that answers it. Okay. All right, let's take a look at 2. Solve this equation. Okay. This secant squared of x minus 2 equals 0 is a trigonometric equation. It's quadratic because there's something squared, but it's missing the linear term. So this is like solving 3r squared plus 2 equals 0. You simply move the 2 over and divide by 3, and then you can take the square root. This would have no solutions because you can't take the square root of a negative, but the point stands. All we need to do here for this equation to begin with is add 2 to both sides, and then take the square root. But what have I done wrong? It's an intentional mistake. What have I done wrong here? That's right, plus or minus. So now I have two equations. And those two equations were ones that could have been assigned yesterday. I'm going to rewrite this equation as cos of x equals 1 over root 2. And I'm going to rewrite this equation as cos of x equals 1 over negative root 2, which is negative 1 over root 2. So I'm prepping this so I can either use my calculator to find a reference angle or think of the unit circle. And I'm going to think of the unit circle. Remember that 1 over root 2 is root 2 over 2. If you want to use your calculator and find a reference angle here, maybe do that right now. Just find a reference angle for either of those equations. And put it in degree mode. How many of you know what the reference angle is without using your calculator? It's 45 degrees, right? These are these numbers that are halfway between, midway between the axes. So if you use the reference angle, you would say, here's my circle. I'm going to put all of them on the same circle. You would say that for cos of x equals 1 over root 2, the reference angle is 45 degrees. I don't know, are we asked to work in degrees here? We are. 45 degrees, and since cosine is positive, it's in quadrant 1 and quadrant 4, where x is positive. So you would draw a terminal arm here, a terminal arm here. For the one where cos of x equals negative 1 over root 2, you'd still get the same reference angle. Because you go inverse cos of 1 over root 2. You don't include the negative in that. But you would say that that is in quadrant 3 and 2. So it would be these two locations. And if this is 45 degrees, and this is 45 degrees, and this is 45 degrees, and this is 45 degrees, you can come up with the rotation angles. The rotation angles would be 45 degrees, 180 minus 45 degrees, 180 minus 45 degrees, 180 plus 45 degrees, 360 minus 45 degrees. You could figure out all of those rotation angles. But that's not how I would do it. I would simply say, if cosine of the rotation angle is root 2 over 2, and I hope you don't mind me switching between 1 over root 2 and root 2 over 2, they're the same number, then on the unit circle, I am looking, on the unit circle, I am looking at this location and this location because that's where x is root 2 over 2. And I just want to make something clear here. Why am I looking at the x coordinate? Is it because there's an x in this equation? Why am I looking at the x coordinate then? Jonathan? No. Well, we are looking for what x is equal to on the unit circle, but my point is the x on the unit circle is not the x in this equation. Because if this said cos theta, we would still be looking at x. So why are we looking at the x coordinate on the unit circle, Marcel? Right, because it's cosine. So, I mean, I could really mess with your head here and give you an equation like this. Cosine of y equals root 2 over 2. You're still going to be looking at the x coordinate on the unit circle because cosine is x over r. So I would, if I were doing this and I had, let me rewrite that again, I have cosine of the rotation angle is root 2 over 2, I would just say it's this and this. And if it's negative, then I would put the two terminal arms in the negative quadrants for x. In either case, and I would go so far as to say, if you understand this, you can do the units. If you understand the unit circle, you can do this. But those four angles will be, going back to the question, 45 degrees. Help me out with my arithmetic here. 180 minus 45 is 135. 180 plus 45 is 225. And 360 minus 45 is 315 degrees. Okay. All right, let's take a look at the third one. Solve this equation. Express your answers to the nearest hundredth of a radian. Okay, so as soon as you see this, you're not going to use the unit circle. You're just going to go with what's on your calculator. We have to factor this first. That bit of business with x in the equation and x on the unit circle being different, if you want to make your life easier on the brain, there is nothing wrong with you saying, I'm going to use theta. I'm going to use theta. I have to admit, if it was a written response question and you changed all the x's to theta without saying that's what you're doing, you might lose something. So if you're going to do this, just say, let x equals theta. What two numbers multiply to give 4 and add to give negative 5? One and 4. Negative 1 and negative 4. So tangent of theta equals 1. Well, tangent of theta minus 1 is 0, which means tangent of theta is 1. Here, tangent of theta minus 4 equals 0, which means tangent of theta equals 4. So what I would like everybody to do is put your calculator into radian mode. We want decimal radian values. Find the reference angle for each of those. I'm getting 0.79 for the first one and 1.33 for the second. Which two quadrants would tangent be positive in? Isaiah? Excellent. Quadrant 1 and 3. Quadrant 1 because, well, tangent is y over x. So y and x, to give us a positive tangent, have to both be positive or both be negative. So quadrant 1 or quadrant 3. I know that most of you are probably capable of just giving me the answers. I'm just going to write 0.8 instead of 0.79. I know that most of you know one of the rotation angles is 0.8, and one will be pi plus 0.8, and you could probably get that without drawing it. But I'm here to serve all of you and not just a few of you. So here, well, we switched it to theta, so I'll go theta equals 0.79. And theta equals, this theta will be pi plus 0.79. Does that work out to 3.93? Pi plus 0.79. Take a look at tangent equals 4. 4 is also a positive number, so we're still looking in quadrant 1 and 3. This time, however, it's a reference angle of 1.33. So we can just add to our list down here. The rotation angle will be 1.33 in quadrant 1, and it will be pi plus 1.33 in quadrant 3, which is 4.47. Thank you. Let's just double check the domain of this question. 0 to 2 pi, we're done. One final question. How's the pace today? Okay. You have a question?
What's the point of having it be labeled as like tan of x if we can just change it to?
It's a good question. If you take a look at the questions in the textbook almost exclusively uses theta. But when you get to diploma exams, they use x. And I think, it's not that there's a point, I think that they use x as an unknown because that's a holdover from everything you've been taught all the way along the way. When you're solving an equation, it's solve for x, solve for x, solve for x. I wish that we exclusively did what the textbook does and use theta. And I want to caution you, the question was, what's the point in using x if we can just change it to theta? You can change it to theta in order to process the math in your head. But really, you know what, Arden, as an answer here, I really should be writing, I really should be writing x. At the beginning of this, if it's a written response, at the beginning of this I should be saying, something like that. Just letting the marker of the written response know I'm more comfortable working with theta. And then at the end saying, since x equals theta, these are not thetas, these are x's. I don't think it's a big deal, but a marker on a diploma exam might. Have I answered your question? Okay. Let's take a look at number 4 now. Solve this equation. Well, it's quadratic, so we're going to zero the equation. 3 sine squared of x plus 2 sine of x is equal to 0. We're in degrees, nearest tenth of a degree. This will be back on more familiar ground for most of us. But there's no constant term, so this goes full circle back to the beginning where I showed you that if there's no constant term, then factor out the common factor. And I can factor sine of x out of 3 sine of x. I can factor sine of x out of 3 sine squared of x to be left with 3 sine of x. And I can factor sine of x out of 2 sine of x to be left with 2. So if I were to multiply the sine of x back in, you can see I would get 3 sine squared of x plus 2 times sine of x, which is where we started. The point of factoring it is now to take each of the factors and set it equal to 0. To turn it into equations we knew how to solve yesterday. The first equation is sine of x equals 0. The second equation is sine of x equals negative 2/3. Personally, I wouldn't need to use my calculator for this. Because I'm dealing with sine, I'm looking at the y coordinate on the unit circle. If you like, if it just makes the thought process that much simpler, because we're going from an equation with a variable to the unit circle that has x in it as well, do that. So I'm looking on the unit circle at where sine is 0. Well, sine is the y coordinate on the unit circle. And the y coordinate is 0 here and here. Guess that doesn't show up on video. The y coordinate is 0 here and here. So what's our domain? 0, we can include 0. So one of our solutions for theta, I'm just going to stick with theta, is 0 degrees. One of them is 180 degrees. Can I use 360? No, because if you look at the domain, 360 is not included. Now, when it comes to this beast, well, not beast, when it comes to this equation, we can't use the unit circle. I don't know where on the unit circle the y coordinate is negative 2/3. It's someplace, but I don't know. So I'm going to find the reference angle. The reference angle will be the inverse sine of 2/3. In degree mode, I want to know how many degrees this is, so it is 41.8 degrees. Remember, you do not use the negative in the reference angle calculation. I look at the fact that sine is negative, so I need to look in quadrant 3, where sine is negative, quadrant 4, where sine is negative, 42 degrees here, and 42 degrees here, gives me this as a rotation, and this as a rotation. And finding those two angles is easy. You know, like a lot of the math in this course, every little step is easy by itself, but you put them all together and there's a lot to remember. If it's in quadrant 3, 180 plus 42 is 222. So 221.8 degrees. And if it's in quadrant 4, it's 360 minus 42, which is 318. So 317.2, I think. So I'm going to give the assignment first, then Ian, you have a question that I will address. On page 212, number 7, 217.21, I think the additional questions, you know, can you just do me a favor and just do a quick flip to there? Yeah, they're just, you know, extra practice. You know how I feel about practice and, quote, homework assignments. Your job is to get better at this. Every time you do a question, you're a little more efficient and better at doing that type of question than you were at doing the previous question. So you guys can get to work on that. You have about approximately 10 to 15 minutes to work on this.